All right, welcome everyone. Our seminar speaker for today is Saugata Basu from Purdue University. He's going to talk about two methods for efficiently approximating semi-algebraic sets up to homotopy by simplicial complexes. So the floor is yours.
Oh, thank you very much, and I really appreciate this opportunity to give a talk at this virtual seminar. So as I was explaining, this talk might be a bit of an outlier in this community because, as far as I understand, most of the work in applied topology tend to start with the input data being some kind of a finite simplicial complex or some cell complex. But here we are going to start with semi-algebraic sets. And so maybe the notion of computing or algorithms in semi-algebraic geometry may not be as familiar to this community. So I'll try to begin with a brief primer on what algorithmic semi-algebraic geometry or topology is about. And then I'll talk about two new results on approximating semi-algebraic sets up to homotopy by finite simplicial complexes. So, okay, and please feel free to interrupt me to ask any questions, because part of my motivation in giving this talk is to familiarize the audience with notions from algorithmic semi-algebraic geometry. So what are the geometric objects? What are the algorithmic problems? And most importantly, what is the definition of complexity of algorithms? Well, throughout this talk, art will represent a real closed field, but which you can just take to be the field of real numbers without any loss. And the input will have coefficients belonging to some domain contained in R, which you might as well assume to be the integer. So all polynomials that appear as input to the algorithms can be assumed to have integer coefficients. But of course, more generally, you can think that these coefficients belong to some arbitrary domain, maybe R itself. Well, then, what is a semi-algebraic set? Well, a basic semi-algebraic set is some subset of finite dimensional reals Rn, which is defined by a conjunction of some finite number of polynomial equalities and inequalities. So things of the form, let me see if I can write. Sorry. I'm trying to get my, pen to write. Okay, I probably should have been a bit more prepared because my pen is not writing, but it doesn't matter. So a basic semi-algebraic set is a subset defined by a conjunction of a finite number of equalities and inequalities, while an arbitrary semi-algebraic set, not necessarily basic, is a finite union of basic semi-algebraic sets. So what's a typical algorithmic question? Well, just to answer, so if you are given some formula so by a first order formula, I mean a formula whose atoms, a Boolean formula whose atoms are polynomial equations and inequations. So you are supposed to answer using only rational arithmetic and comparison amongst in the domain of coefficients, maybe just the integers, and you answer the questions about the semi-algebraic subset that this formula defines. And in this talk, we'll only talk about exact symbolic algorithms, and by complexity, which I will define in a more precise way a little bit later, but it will measure the number of arithmetic operations and comparisons in this domain D. Now, that this is at all possible, even for the simplest problem. For example, just determining if a system of polynomial equations and inequations in n variables have a real solution, meaning whether R of phi is empty or not. So that's already is not trivial, but this is a consequence of a theorem of Tarski that the first order, in fact, about the decidability of the first order theory of reals, and more generally, the fact that there is a quantified elimination algorithm in the first order theory of reals. So maybe for people in the audience who is not so familiar with quantified elimination, let me point out the example that almost all of us for sure is familiar with. So, so suppose you have a quantified formula. So there exists an x as at x squared plus 2bx plus c equals 0. So modulo the theory of the reals, this quantified formula is equivalent, as we all know, to the quantified free formula in the free variables b and c, namely this one, and minus c. So geometrically, you can think of the elimination of this existential quantifier as the projection of the subset in R3 in the x, b, c space, defined by the equation x squared plus 2bx plus c equals 0, to the R2, the b space spanned by b, the variables b and c. And Tarski's theorem tells you that in geometric language, that the image under such a projection of a semi-algebraic set is again semi-algebraic. So that's pretty simple, but note already that if you take the quadratic or the quartic analog, so if you take the formula that there exists x such that x to the fourth plus ax squared plus bx plus c equals 0, and you ask what is the quantifier free expression, well, Tarski's theorem assures us there is one, and here is one description of it, which the fonts are too small, and I don't expect you to read what these polynomials are, but it's rather a complicated formula to describe the semi-algebraic set. So is saying that the semi-algebraic set described without quantifiers is the set of all ABC, says that the corresponding quadratic equation has a real solution. Actually, though, if you, in this ABC space, if you ask what is the set of such ABC for which the quadratic has a real solution, the discriminant hypersurface is looks quite simple. So this is for those of you who know what discriminant is the discriminant of in the ABC space. It has a name, it's called a swallowtail. And if you look at it carefully, the various regions, so the complement of the discriminant is disconnected, and the various regions are labeled with the number of real roots. So inside this triangle here, let me try once more. Okay. Oh, it is working. Okay, good. So inside this the region here, the number of real roots is 4. Inside here, the number of real roots is 2, and the number of real roots is 0. But to describe the union of those two regions where there are real roots, it needs a complicated formula involving other inequalities that I displayed in the last slide. Okay. So that's just about some quantifier elimination. But we could ask more complicated questions given a description of a semi-algebraic set. For example, can you compute its topological invariance, such as its Betti numbers, or the Euler form characteristic, or the number of connected components? Suppose you are given a semi-algebraic map, can you compute effectively the homology functor for such semi-algebraic map? And then maybe more to the interests in this community, but of which I'll not mention too much in this talk. If you are given a filtration of a semi-algebraic set by the sublevel sets of some semi-algebraic function or some polynomial, can you compute the persistent, the barcodes of such a filtration? Of course, these barcodes will have endpoints which are algebraic numbers. And so you'll have to deal with the problem of how to represent such algebraic numbers. If you have a semi-algebraic set with group action, then you can also ask for computing its equivariant Betti numbers. The reason I listed these problems is because there's been recent work on each one of them for developing algorithms for computing these invariants. But you can think of other problems. Now, just a little bit from the point of view of motivation, I want to say something about why study these questions in this exact model, as opposed to, let's say, numerical algorithms, which are often the algorithms of choice in practice. So in this field, what one means by numerical algorithms are algorithms whose complexities are not uniformly bounded in terms of the size of the input, but depends also on some condition, which is typically a real parameter. And this, so that means that the algorithm is allowed to fail if this condition, if it is ill-conditioned, but normally it should run efficiently in the input parameters and in this condition number. So there has been quite a bit of recent work on computing Betti numbers of semi-algebraic sets in this kind of setup, in which you are allowed to fail if you are given a singular variety, condition number is infinite, but otherwise the algorithm would compute in complexity, which depends on the condition number. And this may be good enough for many applications. On the other hand, exact algorithms reflect more the algebraic structure of the problems. So for the algorithms which depend on condition number are, for example, will not see or deal with singularities, for example. And if we take this domain D to be R, then our model corresponds to the Bloom-Schupf-Smale model of computation. And also studying exact complexity is important from the point of view of complexity theory. So, so there are some connections with discrete classical complexity theory, for example, Tora's theorem, and the kind of complexity that I'm going to be discussing today. And also it's important in view of some recent work on something called existential R hardness questions in discrete and computational geometry. So these should be thought of as kind of the version of NP hardness extended to reals that seems to be relevant in this community of discrete and computational geometry. So anyway, so this is just some motivation for talking about exact algebraic symbolic algorithms. So a recent problem of this illustrative example of existential hardness is these nice paper, and there are several of them about this ER completeness, which seems to be very relevant for studying hardness of geometric problems. Okay, so I've been talking about complexity and so on. So, and by complexity, as I explained before, we mean the number of arithmetic operations in amongst the coefficients and comparisons in the domain D. So, but for a given problem, so if you have a formula that's an input, and then the only polynomials that appear in the formula, suppose, is belongs to a finite set P, then we'll call such a formula P formula. And moreover, if this formula only has weak inequalities and no negations, so this means that it's in, let's say, in disjunctive normal form, no negations and only weak inequalities, then it obviously defines a closed semi-algebraic set, and we'll call such a formula to be a P-closed formula. So a P-closed formula only have inequalities coming from this family of polynomial P, and only weak inequalities are allowed. And typically, the complexity of algorithms will be bounded in terms of 3 parameters. There's a combinatorial parameter, which we'll always denote by S. That's the cardinality of the number of polynomials that appear in your formula. And then it will have to depend on some algebraic quantity, which you take to be the maximum degree amongst the polynomials that appear, and K, the number of variables. So these 3, S, D, and K would, the complexity would be a function of S, D, and K. Now, in semi-algebraic geometry, there are kind of 3 levels of complexity that one sees for the standard problems that I've listed. So the problem of quantifier elimination in general, that if you are given a quantified formula and you want to compute equivalent quantifier-free formula, its complexity is doubly exponential in K, the number of variables. The same goes for the best known algorithm for computing semi-algebraic triangulation. By the way, for quantifier elimination in general, this doubly exponential dependence is also unavoidable. So there is a lower bound. For semi-algebraic triangulation, which are listed as an open problem, we do not know whether this is the best you can do or not. And then there are problems for which we know singly exponential. And by singly exponential, I will mean a complexity of this form where the exponent is a polynomial in K. Sometimes this polynomial is even linear or quadratic, and it's not really as bad as K raised to some undetermined constant, but in general, I'll call such a complexity singly exponential. And the problems for which we know singly exponential algorithms are quantifier elimination if the number of alternations of quantifiers is fixed. So you could have many variables that you want to eliminate, but the number of blocks of quantifiers is bounded by some constant. And then certain topological invariants, like we know how to compute the Euler-Poincare characteristic, or we know how to compute for each L, which if you fix the L, the first L Berry numbers for each fixed L. So these problems, we know algorithms with singly exponential complexity. And then there are algorithms which are even polynomial in all the parameters. By the way, in the previous few, the doubly exponential, singly exponential, if the number of variables is fixed, then of course in the other parameters these are polynomial. But so there are certain algorithms for which are polynomial in all the three parameters, and these include, for example, if you want to decide whether a semi-algebraic set defined by few quadratic inequalities is empty or not, then it can be done in polynomial complexity, polynomial in a number of variables. Computing, if you're given a symmetric semi-algebraic set defined by symmetric polynomials of some fixed degree, so degree bounded by some fixed constant, then computing the equivariant Betti numbers is also polynomial complexity. And same goes for computing the first L-Betti numbers of semi-algebraic set defined by symmetric polynomials of fixed degrees. All these are not obvious, and it requires analyzing the geometry and topology of these semi-algebraic, special properties of these semi-algebraic sets. And I'm not going to talk more about them, but just to give an idea of what the hierarchy of complexity results that one has. Okay. So today, mostly, I'm going to go back to this question, because if you want to compute topological invariance of semi-algebraic set, one way is to reduce it to a combinatorial topology problem of computing topological invariance of some finite simplicial complex. And it is a well-known theorem in semi-algebraic geometry that every closed and bounded semi-algebraic set admits a semi-algebraic triangulation, meaning that there exists a there exists a finite simplicial complex K and a semi-algebraic homeomorphism H from the polyhedron of K to S. And once, of course, once you have such K, which is a finite simplicial complex, then computing all topological invariance of S boils down to computing those of K. For example, if you want to compute homotopy groups or the Betti numbers, boils down to dealing with finite simplicial complex. There is an effective algorithm, so not just there exists semi-algebraic triangulation, but there is an effective algorithm of computing such a semi-algebraic triangulation via a technique which is plays a very important role in semi-algebraic geometry, which is called a cylindrical algebraic decomposition. I will not define what a cylindrical algebraic decomposition is precisely of Rk adapted to a given semi-algebraic set, but I believe I have a picture coming up which will just give you an idea of what it is. However, the problem is that the complexity of this algorithm, okay, here's the picture. So what is a cylindrical decomposition of Rk adapted to a given family? Well, this is a picture of a cylindrical decomposition of R3 adapted to the unit sphere in R3, or any sphere in R3. So the data for a cylindrical decomposition, so of course it depends on the choice of coordinates, as you can see from the picture. So you have the projection here from R3 to R2. And the cylindrical decomposition is defined in an inductive way. So first of all, you have a decomposition of R1, which is shown in this picture here. So this is a decomposition of R1 into open intervals and points. So there are 2 points and open intervals. So there are 3 open intervals. And then there is a decomposition of R2, which is shown in the plane. And what is this decomposition of R2? Well, once you have a decomposition of R1, over each cell of R1, so for example, over this cell, you have a certain number of semi-algebraic continuous functions whose graphs are shown. So this is the graph of one of them, and that's the graph of the other, which are ordered And the cylindrical cells of the decomposition, instead of being intervals and points for R1, are either the graph or the region which is in between the two graphs. So that's one region, that's another region, that's semi-infinite, and that's another region that's semi-infinite, right? So, and this is another region. So you get a cylindrical decomposition of R2. And now, once you have the cylindrical decomposition of R2, you lift it to a cylindrical decomposition of R3 in the obvious way. So now, over each cell of the cylindrical decomposition of R2, you will have continuous semi-algebraic functions, which would be over this particular cell. It would be the graphs of these semi-algebraic functions will be the top and the bottom hemisphere. So that's one graph, and that's the other graph. And you have a cylindrical decomposition of R3 adapted to the sphere. What does it mean, adapted to the sphere? It means that every cell of the cylindrical decomposition of R3 that I just defined is either contained in the sphere or disjoint from it. So the sphere is a union of some of these cells of the cylindrical decomposition. Now, once you have this cylindrical decomposition, which is not a simplicial complex, then it is possible using something like a scalar subdivision to refine it to produce an actual triangulation of a semi-algebraic set. It's technical, but that's possible. But the problem with the cylindrical decomposition is that the complexity of doing it, producing this, it involves a squaring of the number of polynomials and the degrees at each step of this projection. And it gives you a simplicial complex whose size would be bounded by a doubly exponential complexity. And even worse, if you, for example, if you are interested in only the number of connected components or some small dimensional homology, so you produce a triangulation and you're only interested in the kind of these first few Betti numbers, which just depends on the low dimensional skeleton of the triangulation. But this upper bound is not sensitive to the dimension. So even if you are only interested in the zero-dimensional homology, which you'd be able to obtain if just looking at one skeleton of the triangulation, but the cylindrical decomposition would produce a simplicial complex whose one skeleton is already doubly exponential in size. That's computing even the zero-th Betti number using a cylindrical decomposition has the same complexity as computing all the Betti numbers, at least in the worst case. However, you might ask, does it have to be this large? And in fact, there are upper bounds on the Betti numbers of semi-algebraic sets. And these are usually proved using some version of the critical point method, which in the smooth case is just Morse theory. And there's this theorem which has a long history in the sense that it has been proved in steps. But what we know is that if S is a P semi-algebraic set, need not be even closed, so some arbitrary P semi-algebraic set, then the sum of the Betti numbers of S is bounded singly exponentially in K. In fact, and this big O here is hiding not a very big constant, maybe just about 2. So the sum of the Betti numbers is bounded by this singly exponential bound. So then one can wonder, and by the way, I said this bound has some history. So that's a list of developments which leads up to this bound, but the final result in which I have stated appears in this paper of Gabriela and Borovjov. The main contribution in this paper was to reduce the arbitrary case to the case of a P-closed semi-algebraic set, which already is not so simple. Okay, but coming back to the algorithmic question, computing triangulation takes doubly exponential complexity using the cylindrical decomposition, but we know that the Betti number is singly exponential bound. Maybe one should be able to compute a better triangulation, which more reflects the upper bound of the Betti numbers rather than this upper bound of doubly exponential, which is coming from this inductive way of building the cylindrical algebraic decomposition. So here's an outstanding open question of which I don't know the answer to, but we have been open for many years. So is there an algorithm with singly exponential complexity for computing a semi-algebraic triangulation, and hence for computing all the Betti numbers of a given semi-algebraic set? Okay. So since we do not know the answer to that question, maybe we should look for something weaker. Semi-algebraic triangulation, of course, encodes information about all homeomorphism invariants, which may be difficult to compute. So maybe we can ask a weaker question that can you compute a simplicial complex whose geometric realization is homotopy equivalent? And maybe now we can produce a simplicial complex which is singly exponential in size. And then all homotopy questions about all homotopy invariants of your given semi-algebraic set can now be asked of these finite simplicial complex. And that would already be good enough for example, computing the Betti numbers in singly exponential complexity, which is also not known. Unfortunately, this is also open and we do not know how to do it. Computing a simplicial complex, which is semi-algebraically homotopy equivalent to the given semi-algebraic set. So these are all somewhat negative news. So I will say something now about new results which are positive. And in the title, maybe the title was a bit misleading because I said two approaches. But the second, this internal approach is more of ongoing work than actual result. But anyway, let me say what do I mean by an external and an internal approach. So the external approach would be in the vein of this weaker question. So compute semi-algebraic simplicial complex, which is homotopy equivalent to a given semi-algebraic set, which we do not know how to do. But suppose I weaken it even further and say, well, compute a simplicial complex that's only L equivalent to your given semi-algebraic set. So it encodes information, homotopy information up to dimension L for some fixed L. So that's this corresponds to this external approach because this simplicial complex it will not correspond to some it will not be a triangulation of set itself. So it will be some abstract simplicial complex whose polyhedron has some homotopy properties of your given semi-algebraic set. But then you might ask that, well, can you compute, suppose I'm only interested in homotopy up to dimension L or homology up to dimension L. Can you compute L-dimensional semi-algebraic subset of your given semi-algebraic set such that the inclusion is an L equivalence? So up to dimension L or L minus 1, I would be able to just look at this small dimensional semi-algebraic set and deduce homological information. By the way, that's not possible using triangulation because of what I mentioned before, that the fact that the upper bound of the triangulation is not sensitive to dimension. So even if you are interested in the zero-dimensional homology, the triangulation will produce a complex that's whose one skeleton is already doubly exponential in size. So what I'm asking here is that can you produce a complex which will not be the one skeleton of a triangulation, but which would be one equivalent to the given semi-algebraic set. So this is what I mean by an internal approach. Okay, so we can do this. We can solve this weak version, meaning produce a simplicial complex which is L equivalent. So this is a result with my ex-student Negin Karisani, and which we call simplicial replacement. So I want to give a basic idea of where it comes from. So let's fix some L, which is the dimension up to which we would like to study the homotopy or homology of given semi-algebraic set. And there's this hypothesis, which says that suppose that there exists algorithm with singly exponential complexity that given any closed and bounded semi-algebraic set as input, of course, when I say as input, I mean a description of it as input, it produces a cover of S by closed and bounded L-connected semi-algebraic sets. By L-connected, I mean that it's non-empty, it's connected, and the homology vanishes up to dimension L. Homology in dimension bigger than 0. Now, this hypothesis is not an arbitrary hypothesis because we do know that there exists such an algorithm with taking L even to be equal to infinity. So we know an algorithm for computing a cover of a semi-algebraic set by contractible semi-algebraic sets. So this was a basic building block of work that I did with Ricky Pollack and Mark Francois from maybe over 12, 14 years ago. So it appears there. So our theorem is that, but of course, maybe someone more clever can come up with a black box algorithm for computing with a better complexity cover of L-connected, not necessarily even contractible. We only know one which is contractible, but maybe there exist better algorithms for computing covers with a weaker hypothesis. And our theorem is that if we assume this black box hypothesis, which we are allowed to assume because there exist such algorithms for computing contractible covers, then there exists a single exponential complexity algorithm that, given a closed and bounded semi-algebraic set, produces a simplicial complex, which is L equivalent, meaning that there exists a diagram like this, and where the F1 and F2 induce isomorphisms in homotopy groups up to dimension L. And here X is some closed and bounded semi-algebraic set. So all, if you are interested in homotopy information of S up to dimension L, now you have to solve this problem for the simplicial complex, but this simplicial complex is of singly exponential complexity, other compared to doubly exponential, which you get by taking the L skeleton of semi-algebraic triangulation. So maybe I just explained the main idea through an example. So we are going to use these coverings, and the coverings should remind you of the Nernst lemma, except that when we compute this covering by contractible sets, semi-algebraic sets, we have no control over how on the intersection. So the intersections can be very complicated. But we can again apply the covering algorithm to the intersections. And then we'll produce another cover, but the intersections can again be complicated and so on. So here's an example of how the algorithm actually works. Of course, it needs to be justified, which I'm not going to do in this talk. But suppose you take the case of a sphere in two sphere, and then your covering produces two hemispheres, the S1 and S2. So these are contractible, but their intersection is not, which is the circle. And you apply the covering algorithm again, and it produces, let's say, a covering, because this is a black box hypothesis, a covering of the circle by these two semicircles. And their intersection is again not contractible, but then there's just 2 points. The covering algorithm, let's say, just produces these 2 points. So in this simple example, it happens to be that if you now look in this poset, which I've drawn here, so the subscripts in this poset corresponds to the numbers in this poset in the Hasse diagram corresponds to the subscripts of these sets that are appearing in the covering. And then you look at the simplicial complex associated to the poset, meaning the whose simplices are all the chains. Then this simplicial complex does have the same homotopy type, and in this case, it actually is homotopy equivalent or even homeomorphic to the sphere. So, the actual algorithm proceeds in this way, but you'll have to keep track of the number of sets that you are producing in these coverings, and you have to prove that you only have to go down these intersections up to maybe up to a level L, which is L, the dimension that you have fixed, and that the so we produce a poset which looks like this, whose associated simplicial complex, the order complex as it's usually called, is a L equivalent to the given semi-algebraic set that we started with. And we only need to assume that the covers consist of sets which are L connected, not necessarily contractible as in this picture. So you can, paper is on the archive and you can look at it. So this is the precise theorem that there exists an algorithm without a black box hypothesis, because we know such a black box, which takes as input a P-closed formula and as produces an output simplicial complex, which is L equivalent according to the definition in the previous slide. And the complexity of this algorithm is singly exponential in the sense that this polynomial is polynomial if L is fixed. So it's better than taking the L skeleton of semi-algebraic triangulation. Maybe since I was supposed to talk only for 40 minutes, I'm probably out of time here. Maybe
no, we can take some more time. So we have until the hour, and then people typically start leaving because they might have other engagements. But please feel free to continue.
Okay. So thanks. So one question that you can ask also in this vein is that, okay, you have been talking about homology. So the internal approach would be to approximate homotopically a given semi-algebraic set by some subset of a small dimension. And then one could also ask that, can you produce a semi-algebraic basis of the small dimensional homology of a given semi-algebraic set. So, as I've said, the internal approach is about trying to compute an L-dimensional semi-algebraic subset, so the inclusion map is an L equivalence. And it's of course possible using semi-algebraic triangulation, but it's doubly exponential, of course, because even the number of vertices in a semi-algebraic triangulation, there's no way of controlling given the current state of knowledge. Now, this problem for the zero-dimensional case, so that means computing a point, a unique point, one point in each connected component of a given semi-algebraic set. So that problem is solved and is well known. It's one of the very first problems that one deals with in semi-algebraic, algorithmic semi-algebraic geometry of computing a set of points which meets every connected component in exactly one point. And there exists singly exponential complexity algorithm that does that. And you can interpret this set of points as semi-algebraic basis of the zero-eth homology of the given semi-algebraic set. And just to say how that goes, it actually goes in two steps. One first computes, so this is an easier problem. That so this is usually sometimes called sample points. So you can compute using some critical point method, which is some beefed up version of Morse theory, and compute a finite subset of your given semi-algebraic set, which you call sample points, which is guaranteed to meet every semi-algebraically connected component of S. In homological terms, this means that the map from H0 of gamma to H0 of X is guaranteed to be surjective. And this problem is a building block for efficient algorithms for solving quantifier elimination problems that I was referring to in the beginning of the talk. So that produces maybe an overcount. And then if you want to pare it down such that you have exactly one point in every connected component, then that's also possible. And that goes via a very key idea, which is the notion of a roadmap of a semi-algebraic set. So I'm not going to define what a roadmap is, but it is some one-dimensional subset which is allowed to contain any finite set of points, and that's from which, and in fact, this subset has additional property that is connected inside every connected component of S. And so once you have this subset containing two given points, then it's easy to decide whether these 2 points belong to the same connected component of gamma and hence of S. So just to summarize, to produce a point, unique point in each connected component, you first produce a finite set of points which is only guaranteed to meet every connected component, and then use the roadmap algorithm for computing a basis of the H0. So, and there's a, as I said, there's a long history of producing roadmaps of semi-algebraic sets. But what about the higher homology? And so maybe I'll mention this new theorem, which is worked with Sarah Percival, also ex-student with me, which says that you can do the one-dimensional analog of the previous. So in the sense that if you're given a semi-algebraic set, we are able to compute a set of curves, gamma j, such that the images in the one-dimensional homology that these gamma j's represent forms a basis of H1 of S. Just like in the previous case, the sample points pared down after step 2 was the basis for H0 of S. And it's interesting, you can find this paper on the archive. It's called Efficient Computational Semi-Algebraic Basis of the first homology group. And it's interesting that the algorithm follows the same two steps. So we first compute, instead of a set of zero-dimensional set of sample points, we compute a one-dimensional subset such that in the first homology, there is, so this homology is surjective, and it's isomorphism in H0. So this is surjective, and that's an isomorphism. So this is analogous to the first step in the zero-dimensional case. And in step 2, we have a way of deciding whether we choose a basis of this gamma, the H1 of this gamma, and then we have a way of producing a basis of S, or H1 of S from this basis of H1 of gamma. So maybe I'm not explaining this in proper details, but the main takeaway idea is that we can do in one dimension or what was classical in the zero-dimensional case, namely this one. Okay, so maybe let me just end with conjecture about this internal. So I believe what should be possible is, so this is, if this is possible, this would be an internal approximation up to some fixed dimension of a given semi-algebraic set. And the conjecture is that suppose you're given a semi-algebraic set defined by a closed formula of some complexity of dimension n, then you should be able to find subsets of Z sub I of dimension at most I, such that the homology of the pair is 0 for in dimension 0 to I. So that means the Z sub I is an I-dimensional approximation up to homology of X. And moreover, and which is important, so of course you can do that by taking Z sub I to be the I skeleton of the triangulation. But what we would also want is that the complexity of Zi is bounded polynomially, where bounded singly exponentially, where this exponent here is a polynomial which is of degree which is growing with I. So in the worst case, if you take I to be equal to, oh, by the way, this K should be an N, sorry. In the worst case, you will get something that's doubly exponential. But for fixed L, you will obtain internal approximation of X by something that is singly exponential of this form. So in the way I've written, this should be C raised to N raised to of L rather than K. So this would be kind of the internal analog of the Simplicial replacement using covers. And the idea being that you should be able to find low dimensional homological or even homotopical information should be easier to compute than the total homotopy of a given semi-algebraic set. So what I presented for the basis of the first dimensional homology allows us to do this up to dimension 1, but I believe that it can be extended to higher dimensions, maybe using ideas that are already there in this paper, but we have not done that yet. So that's the internal analog of approximating. Okay, so let me end now, and I'm happy to take any questions if there are questions.
All right, thank you very much. Before we stop this, let's maybe quickly unmute and clap for Saugata. Thank you very much. All right, are there, I mean, we are already approaching a little bit the hour, so I'm wondering, is there are there any public questions that we want to have for the public section of this discussion?
Maybe the semi-algebraic geometry was a bit heavy but I just wanted to give an idea of the kind of state of the art in this field.
No, this is great. I have a very naive question about this, but so you already alluded to some to this conjecture, right?
Yes.
Where do you see kind of other open questions with respect to this? Is there something that that you're interested directly in tackling next, going beyond that specific conjecture here?
Yeah, so there's several things. So for example, I would really like to settle this conjecture, which I think is doable. There will be a lot of technical abstractions using the ideas from this one-dimensional case. And this would kind of give actual content to the intuitive feeling that we have that the small dimensional topological information should be easier than something in the middle. That's one side. And then there is some other things that I did not mention, which is part of ongoing work, but also interesting, is that, and maybe relevant more to this community, is the topic of persistent homology for filtrations of semi-algebraic sets by polynomial functions and multi-persistence. So if you're looking at some filtration of sublevel sets by more than one polynomial of a semi-algebraic set, and then there is this multi-persistent modules, and then it's of course people are studying various things about multi-persistence. What's a right notion of our generalization of a notion of a barcode, how to extract some finite information from these multi-persistent modules. All these questions are harder because of algebraic difficulties and not knowing a structured theorem for irreducible multi-persistent modules. But it's even harder now in the setup of semi-algebraic filtration, so that the indexing, the values are now coming from real numbers. And so some of the things that I have mentioned, like for example, how to compute, what does it even mean to compute this functor? So to compute homology, as we all know, is a functor. So so typically the question should not be compute the Betti numbers from a semi-algebraic set, but to compute a description of the homology functor of a given semi-algebraic map. And these are kind of, in my mind, are building blocks to developing notion of a semi-algebraic barcodes computationally in this exact setup that I was talking about in this talk. So this barcode should be some kind of a constructible function on this space of that you are in. But okay, so I don't want to say hand wave too much, but that's the kind of direction which I'm really very much interested in.
No, this is really
things
cool.
that we talk about here are kind of, in my mind, are building blocks to develop.
No, I agree with this. I mean, this is fascinating. I mean, I have never thought about this. To be perfectly honest, that one can extend persistent homology to this setting as well. So this is really very exciting stuff for me. So if there are no other public questions, then I am going to stop the recording here.